So the next talk is by Nate Harman, and he will talk about stability and periodicity in modular representation theory.
All right, great. Thanks for having me. I do want to warn everyone that I've been having some internet troubles, so I hope I'll make it through this talk without getting kicked off the internet. But if it does happen, it seems to only last about a minute, so I'll come right back. All right, yeah, so I'm going to talk about stability and periodicity in modular representation theory. And well, so I guess I just want to say kind of about me and my research. Sort of everything that I do has some sort of modular representation theory component to it. But I think sort of typically I'm sort of interested in questions that maybe involve modular representation theory, but that's not maybe the motivation for the questions always. So I think this will be sort of a little bit orthogonal direction to a lot of things that I know people here think about. But so yeah, so I decided just to sort of give maybe an overview of one kind of story like that, of something that I work on a lot and kind of highlight the kind of modular representation theory aspects of it. So all right, let me get started. So I want to talk about stability phenomena in representation theory. And let me say a bit what I mean by that. So in representation theory, right, we often have kind of, we don't really care about all groups and all algebras a lot of the time. There's sort of nice families of those that we care about more than others. And in particular, families that are often happen to be indexed by a natural number. And so, for example, we could look at, general linear groups over the complex numbers, symmetric groups, orthogonal groups, finite general linear groups, that Hn of Q, I mean the sort of Hecke algebra in type A, quantum groups, sort of these arithmetic groups like sp2nz. I could continue this list on and on. So this is kind of often the case that we care about groups and algebras and other algebraic structures that live in families. And then by stability phenomenon, I really mean sort of as n increases in one of these families, it is often the case that sort of the representation theory stabilizes. It kind of stops depending on n in some sense, or sort of maybe only mildly once n is large enough. And so I want to sort of show some examples of what I mean, because this is a sort of vague formulation, but it's the sort of thing that once if you see it and you can recognize it as being stability phenomenon, even if there's not a sort of precise notion of what stability phenomenon is. But all right, so I want to start with maybe the most kind of classical, well-known example of this. So this is just polynomial representations of GLN just over complex numbers. So this should hopefully be familiar to everyone. So if we take just the defining representation of GLNC, right? So just the matrix representation, and we take its dth tensor power, so tensor with itself d times, GLN still acting sort of diagonally, then the symmetric group acts on this by permuting the tensor factors, and that action, commutes with the action of GLNC. Okay, so this, fine. Then what can we do with that? Well, if we fix now an element of our group algebra for the symmetric group, we can associate to it some subspaces or quotients of this tensor power, right? So the kernel, the image, and the co-kernel, right? Those are all vector spaces that carry a GLNC representation. And now I want to get to this kind of stabilization notion where I'm going to vary n, and sort of the key fact is that for whatever fixed sigma fixed element of my group algebra, I can look at what these are as representations of GLN, and the answer doesn't really depend on n that much. So the irreducible polynomial representations of GLN are labeled by partitions, and for each one of these three subspaces, that decomposition to irreducibles and the multiplicities that show up stops depending on n once n is large enough. It needs to be at least d. So that's kind of what I mean by stabilization. So the answer really doesn't depend on this variable n anymore past a certain point. And then in a related way, if we look at the dimensions of these spaces, they're all polynomial in n. So this is what I mean by sort of, it depends on n, but maybe in some mild way, some sort of controlled way. So being polynomial in n, I want to think of as sort of a mild dependence on n. Right, and this, like I said, hopefully this shouldn't be too shocking to anyone. In particular, if I take my sigma to be a central idempotent, then this is just projecting onto an isotypic component. And that's maybe a more sort of orthodox formulation of Schur-Weil duality. So this is maybe a kind of a more, functorial version of Schur-Weil duality. But the real point here that I want to highlight is that this kind of independence of n past some point. All right, so that's maybe the most kind of familiar example of stability phenomena. And now I want to talk about kind of the analogous thing, but for symmetric groups. So for GLN, we had kind of this labeling by partitions, which is really the same as kind of dominant polynomial weights, highest weights. For symmetric groups, we sort of normally want to index our representations by partitions of n, but I want to sort of renormalize in a way that it doesn't depend on n. And so I have this notation, lambda of n, and what that means is you just take your partition of some arbitrary size and you just put a row on top of it to make it have total size n. Right, so this is kind of a relabeling of the irreducible representations of symmetric groups that's somehow uniform in n in kind of a different way. So for example, under this labeling, the trivial representation for each value of n is labeled by the empty partition kind of bracket n. And the reflection representation is now labeled by kind of a partition 1, a single block, and then we sort of stabilize by adding this top row. Okay, so that's just a sort of combinatorial relabeling of our representations. But why am I doing this? Well, kind of similarly to what we had for general linear groups, if I take, say, my standard n-dimensional representation of Sn, and I take a tensor power of it, well, that decomposition no longer depends on n once n is large enough, kind of under this relabeling, right? So these multiplicities an stabilize as n gets large. All right, so that's sort of the right relabeling to make kind of stabilization work. And again, the dimension of these irreducibles is polynomial in n. So once n is large enough that this kind of partition makes sense, the dimension becomes just a polynomial. All right, and then you could ask, okay, well, what about sort of other representation theoretic operations I could do with these sort of stable symmetric group representations. And well, it's sort of classical that the tensor product multiplicities, which are called Kronecker coefficients, and the Litter-Richardson coefficients, which govern induction and restriction kind of between symmetric groups, these also stabilize as n goes to infinity under this labeling. All right. So this is kind of what I mean. These are the two kind of prototypical examples of stability phenomena in representation theory. And one thing I want to say kind of at this point, nothing here is new. So this fact that these Kronecker coefficients stabilize as n goes to infinity, this was observed in the 30s by Murnaghan. And kind of the GLN stuff is also very classical. And there were, analogs studied by representation theorists for, say, classical families of Lie groups and stuff, 30 plus years ago. So that this all is sort of not really new observations to representation theorists. But what I want to say next is kind of a new thing or a new interest in these things. So that's the theory of FI modules and representation stability. So FI is a category. So it's the category of finite sets and injections between them. And then an FI module is a functor from that to vector spaces over some field, or even often just an Noetherian ring. So maybe kind of one thing to think about is if I just took, n element sets and injections between them, then a functor from that category to vector spaces is the same thing as a representation of Sn. So this, just from that, you can see that this is going to have something to do with representations of different symmetric groups. And that's exactly what I'm saying here. So if we evaluate this just on kind of the simplest chain of finite sets included in one another that we can come up with, this gives us a sequence of vector spaces and maps between them. And so the map from say V2 to V3 is S2 equivariant. And there's some compatibility constraints between them. So while this definition in terms of finite sets and injections is nice, sort of from my perspective as a representation theorist, I really like to think of these as sort of sequences of representations of symmetric groups with some maps between them and compatibility conditions that they satisfy. All right, so what does this have to do with this notion of stability that I was just talking about? Well, these FI modules, they were defined by Church, Ellenberg, and Farb, maybe like 6 or 7 years ago now. And their theorem is that if they have one of these FI modules and it's finitely generated, which is, well, the only possible notion of finite generation you could write down is the right one. So a finitely generated FI module over a field of characteristic 0, then if we look at these representations, right, so I have this sequence of representations, one for each symmetric group, then the decomposition into irreducibles doesn't depend on n past some point. So I get a representation for each symmetric group, and past some point, they all decompose in kind of a uniform way. I have the same multiplicities up to this sort of funny labeling that I had to do to be uniform across different symmetric groups. All right, so this phenomenon is called representation stability. So that's what's going on there. So Great. So this is, a nice theorem about about Fi modules and kind of what they are as sequences of symmetric group representations. But I want to say sort of the real main theorem about Fi modules, the real reason that they're interesting, and if you read kind of this original paper they're defined, what most of the paper is showing that they just appear kind of in the wild. That this isn't just some definition of I'm looking for functors from this category of finite sets with injections. It's that it's a natural algebraic structure that arises in a bunch of different places. And so the flagship example that I'm sort of contractually required to talk about is the cohomology of configuration spaces. So let me say that what I mean. So if I take a manifold of dimension at least 2 and of finite type, I mean, really, I just need its homology groups to be finitely generated. But say, the interior of a compact manifold with boundary will do. So nothing too infinite. I can look at the space of points inside that manifold. So the space of n distinct points kind of moving around inside my manifold and not colliding with each other, at least in this most basic version. And then what's the point? What's the theorem? The theorem is that if I look at the cohomology groups of these spaces and I fix a cohomological degree, then as I vary n, these sequences of cohomology groups, they form a finally generated Fi module. And then in particular, they satisfy this sort of multiplicity stability that I wrote on the last slide. And sort of moreover, this multiplicity stability kind of trivially implies that you have polynomial dimensions as well. Well, I said each one of these irreducibles has polynomial dimension in n. So these configuration spaces, what we get out of this is that the cohomology kind of grows polynomially in n, and moreover, as a representation of symmetric groups, the description is sort of independent of n once this number of points is sort of sufficiently large compared to your cohomological degree. All right, so that's the sort of most celebrated example in this theory of Fi modules, and it's the easiest one that I can just state concisely on a slide. But there are a bunch more, and so I want to just kind of run through a bunch of them just to maybe give you a feel for where these things show up and maybe why people are interested in them. So I'll say some of these are genuinely where Fi modules, and some of them they're sort of relatives of Fi modules with similar family of ideas. So I already said configuration spaces, but the homology of congruent subgroups, syzygies of Segre embeddings, Orlik-Solomon algebras of hyperplane arrangements, some combinatorics of the card game set, spaces of commuting matrices in Lie groups, both fixed Lie groups and varying Lie groups have been studied. The cohomology of Springer varieties, the homology of, so MGN bar, that's the Deligne-Mumford compactification of the moduli space of n-pointed genus G curves. And the homology of the so-called Torelli subgroups in surface mapping class groups and in the automorphism groups of free groups. So those are sort of interesting subgroups that kind of maybe geometric group theorists care about, and the homology kind of has a sort of representation stability type thing on them. All right, so these are just kind of more for motivation for why one might care about these FI modules and their variants. But now I want to say, I want to transition to talking about positive characteristic and modular representations. So I want to start again with a familiar example. So now let's do kind of the same thing that I started with, but in characteristic P. So I want to look at representations of GLN, you know, the algebraic group, and I'm going to look at you know, its defining representation and take tensor powers of that. Just like in characteristic 0, we get an action of the symmetric group. And just like in characteristic 0, we can associate to it some spaces. You know, the kernel, the image, the co-kernel. And just like characteristic 0, these have polynomial dimensions and their composition factors are independent of n for n large enough. So I sort of say that here. I don't know why I broke it up that way. It's bad slide design. So this is an example of sort of stability in characteristic P. So this, what I just outlined, these are examples of polynomial functors. And there's a nice theory of polynomial functors in characteristic P. And the point is polynomial functors stabilize in n in this sense. So the kind of the polynomial representation theory of GLN in characteristic P kind of doesn't depend on n once n is large enough sort of compared to the degree of the representation. That doesn't mean it's easy to understand. There's still, of course, lots of subtleties there, but it just doesn't depend on n. Great. However, something new does happen for GLN in characteristic P, and that's if we look at the adjoint representation, right? So if we look at GLN acting on, you know, n by n matrices by conjugation, something new happens, something kind of different, and that's it really does depend on what n is, kind of relative to P. So if P does not divide n, this space decomposes just like in characteristic 0 as a direct sum of scalar matrices plus trace 0 matrices. But if P divides n, it's actually indecomposable. And kind of the reason is that scalar matrices are trace 0 matrices if P divides n. So we have sort of now a nesting of these subspaces rather than a direct sum decomposition. And so this kind of maybe is the first instance where you might kind of expect the representation theory to sort of depend on n, maybe in some periodic sense. So now it's going to depend on n, what n is mod P, and that indeed is going to be kind of a theme. So I'm going to switch over to talking about the symmetric group case, which I think is sort of maybe the best understood case of this kind of stability and periodicity stuff in positive characteristics. So maybe before I do that, this might be a good place to ask if anyone has any questions.
Are we going to see some porks showing up as dimensions?
Hmm?
Are we going to see some porks showing up as dimensions?
Yeah, so you definitely see some porks showing up as dimensions. Yeah, that's right. I don't know that I'm gonna. Well, yeah, I'll say a bit about that. Great. So yeah, so maybe that's I can just say verbally here. So for GLN, kind of the irreducible highest weight representation with highest weight 1, a bunch of zeros, -1, has dimension n squared minus 1 if p does not divide n, and n squared minus 2 if p does divide n. That's what comes out of this. It's sort of the SLN versus PSLN case. But that's your pork dimensions, Ben. All right, so let's talk about symmetric groups. So what happens in the symmetric group case? And this is something that I worked out a few years ago. So here's what happens. So we take the representations of symmetric groups, and I sort of break it up. I put a filtration on it, and I filter it by sort of complexity, by sort of how far away are you from just the defining n-dimensional representation. So in particular, you could ask, how many tensor powers of the defining representation do you need, maybe with direct sums before the thing you want lies in it as a subquotient. That's actually roughly exactly what these subcategories are. But in particular, it's well behaved with respect to this labeling, this kind of stable labeling of the irreducibles. So in particular, the irreducible and the Speck modules labeled by lambda, if the size of lambda is less than k, lives inside this filtered piece. Right, and that's true for all n kind of large enough such that those partitions actually make sense. Right, so that's kind of what these subcategories are. And then what's the actual theorem? The theorem is that if m and n are sufficiently large and their difference is sufficiently divisible by p, then there's an equivalence of categories between these sort of truncated categories of representations, and it sends Speck modules to Speck modules with the same label. So this kind of initial segment of our category representations, this kind of complexity at most k representations, only really depends on n modulo some power of p. And that power of p, I should say, this f, this explicit function f, it's like roughly, it's just like the next largest power of p, like then k. So if k is less than p, you can take p to the 1. I think that's maybe off by 1, depending if you're near p. I think you might have to go up to p squared. I don't remember exactly, but it's nothing crazy. It's not growing fast. This power p to the f of k is growing sort of like k. All right, so, well, maybe obvious corollary of this is that I have equivalence of categories, and I can phrase the question of decomposition numbers internal to these categories. So my decomposition numbers under this labeling are periodic in n with period a power of p. And that implies then that the dimension of d mu sub n is pork. So there you go. Cool. Okay, so that's sort of the story there.
Could you just recall what is lambda of bracket n? For some reason, I blanked out. I don't remember the definition of.
So lambda is a fixed partition, and then lambda of n is a partition of size n, where I add a first row to lambda.
Okay.
To make it have n total.
Okay. Thank you. Thank you.
So typically, I want to think of lambda as being fixed and small, and n as being very large. All right. So this is a sort of categorical result. But how about what goes on with these FI modules? So kind of part of the motivation for all of this was that these FI modules actually show up So I want to say something about, the cohomology of configuration spaces and all of these other examples. And so interestingly, the answer is sort of a combination of periodic and stable behavior. So let me just, if I have a finally generated FI module in characteristic P, so I'll think of it as a sequence of representations. So first, it's periodic. And it's periodic in the sense that it's compatible with these equivalences of categories I said in the last slide. So for n and m sufficiently large and sufficiently their difference being divisible by p, they get identified. And so if I look at what these are as a representation of a symmetric group, their composition multiplicities agree. And so the composition multiplicities in an FI module become periodic in n, again with a period of power of p. But I also claim that FI modules kind of stabilize in characteristic P. So another kind of separate result of mine is that if we write these inside the Grothendieck ring in terms of Speck modules, and it's not the irreducibles, but the reductions from characteristic 0, that we can write it again in a way where the multiplicities don't depend on n for n large enough. And I should say, there's some ambiguity here because Speck modules are not a basis for K0. There's sort of too many of them. But if you want, you can restrict to lambda being P regular, say, and that will form a basis. Or, well, I think as phrased, there's I have some leeway. Right, but so I have stability in K0, but what I want to say, though, what's important here is that these constants can be negative, and it's easy to come up with examples. So it's not like these FI modules have some filtration by Speck modules. They don't, but still we have at least sort of in terms of K0 or Brouwer characters, they behave like they stabilize similar to characteristic 0. All right, so that's kind of two parts of the story I wanted to tell about symmetric groups in positive characteristic. And there's one more story, and that's stability across characteristic. So far I have been fixing P and letting n go to infinity. And then you could ask, well, what happens if we let both n and p go to infinity? And sort of the answer is that there are lots of ways of doing that, and many of them give uninteresting answers. However, there's one sort of interesting way to do it where we get some sort of new behavior, and that's if we fix a remainder, so we fix some integer k, and then we take n to be congruent to k mod p, but then we let n and p grow. So well, I could make precise, but that is sort of the only interesting way to let n and p go to infinity simultaneously. And if we do that, we get a sort of stability, and the decomposition numbers in this case are independent of the prime. So they sort of only depend on this k and not on p or really what n is, so long as n is congruent to k mod p. So that's kind of just a statement about decomposition numbers. And it's a little weird, right? We're sort of varying the characteristic and the rank numbers. It's really coming from a sort of more categorical statement. And this I really am not gonna unpack for you. There's an equivalence of categories between something called the Deligne category, or rather it's a Abelian envelope, and some sort of limit as p goes to infinity of these categories or representations in characteristic p. So the real, I put it in quotes because this is of course nonsense. This is not, there are no, on the left-hand side, the things that I'm taking a limit of, there's no like functors between these categories or anything like that. So this is not a limit, it's not like a direct limit or inverse limit or anything like that. It's more a limit in the like naive calculus sense of the word limit. But you can make sense of this using model theory. So this is a model theoretic limit, which is maybe weaker than we'd like, but it's strong enough to make conclusions about decomposition numbers. So that's the story for symmetric groups. Kind of in as what stabilizes or becomes periodic for symmetric groups. So I want to just say a bit. So that's kind of the complete thing I wanted to talk about. But now I want to say a bit about what some other families of groups that I think are interesting and some questions kind of in this direction that I think about sometimes and would invite any of you to share your thoughts on. But so I want to say just a bit about some other families of groups and algebras. So all right, for GLN, which I now mean kind of the algebraic group GLN. As we saw, polynomial representations stabilize in any characteristic. The algebraic representations become periodic, and periods of power of p pretty similar to the symmetric group story. And yeah, that's a nice thing. There is a sort of analog of these FI modules for GLN reps that have been defined. And in characteristic 0, they've only actually really been studied in characteristic 0. They satisfy a stability condition. So eventually this decomposition into irreducibles is independent of n. And we expect the same to be the sort of periodicity type things to hold in positive characteristic. It's not known, and it's it seems hard to even formulate. So I will say kind of the problem is there's like a category of FI modules for algebraic representations of GLN, but there's not really the category FI for which it's the modules of. So that kind of throws a wrench in some of the things you might want to do, but there should be a theory there. There should be a nice positive characteristic version where you see some of this periodicity occurring. Cross-characteristic stability, where we let n and p grow, is also known. It's the same type of thing. And interestingly, there's a sort of connection to supergroups. So for supergroups, if I look at GLMN, and now I fix sort of the difference between m and n to be k, I can let m and n go to infinity. And in a sort of suitable sense, there's also a limit there. And they're the same. So kind of these cross-characteristic stable decomposition numbers for representations of GLN are also decomposition numbers for certain supergroup representations. And that is just weird. But again, it passes through these Deligne categories. There's some sort of universal limit, which is maybe why that can be true. And then finally, kind of for this audience, one thing I want to say is this kind of periodicity, maybe both for GLN and for symmetric groups. I would love to understand it in a more sort of geometric way. And that's not to say that there's not kind of geometric components, especially in understanding why it's true for GLN. It kind of very much involves looking at like tilting modules. But I would really love to see it kind of just coming out of some sort of geometric construction. So why why is it that if I take, GLN and I sit it inside GLN plus some big prime power, why do I get kind of a nice embedding of these categories or something, or the truncated ones? So that's kind of mysterious. I'd love to see it explained geometrically. All right, so that's all I want to say for GLN. How about some Hecke algebras and Q-sure algebras? So if we have, the symmetric group story kind of spelled out in detail, we could hope to have to know what's true for Hecke algebras, and most of it goes through the same. So we now have this new number E, which is the order of Q. So right, I'm interested in the the Q a root of unity case. So in characters like P, we have a similar periodicity of these categories, these truncated categories of representations. But now the period we get a secondary period coming from the order of Q. So we still have the sort of P to the K thing that we had for symmetric groups, or P to the F of K or something, some power of P, but we also pick up a period from the order of Q. And in characteristic 0, maybe the more familiar one, that just turns into periodicity of the decomposition numbers with period E. But it's not, there's not a, as far as I know, there's not, some equivalence of categories going from N to N plus E. It's rather, you have sort of a family of categories varying continuously, varying algebraically, and that then things like decomposition numbers have to, there has to be a sort of generic behavior. And so we get this period E thing because it agrees with kind of the generic behavior of that family, but there's not actually, at least at work, there's not nice functors between these categories. And then we could ask, you could let E and N grow comparably. That would be the sort of analog of this cross-characteristic case. I don't know. Numerically, it seems like there's something there. I'm not sure how to make that work, but I think it's an interesting regime to think about sometimes. So I've had some thoughts or guesses of what it might be, but I don't know. All right, let me go on to one more family I want to talk about. So we could also talk about, we could fix Q now to be a prime power, and we could look at GLN FQ, sequence of now finite groups. And so we can get some periodicity of decomposition matrices in non-defining characteristic. And in particular, it's, we can get decomposition numbers for GLN from the Q-sure algebras, but that's the sort of, the kind of triangular part of the decomposition matrix. So we kind of know that there should be some periodicity there, but I don't know what happens for the kind of non-triangular part of the decomposition matrix. Similarly, if we're in defining characteristic, well, at least as far as like the irreducibles and things, we inherit a lot from the underlying algebraic group, but it's still kind of a more complicated story. And one of the things I think is really interesting is that if we look at decomposition numbers, meaning going from characteristic 0 to defining characteristic, as far as I can tell, based on kind of a fairly limited number of calculations that I can actually do, these don't seem to stabilize or become periodic in any reasonable sense. So what do they do is a question I would like to understand. And has been why I joined that SL2 group that we have here. And then kind of finally, I want to say there are analogs of this category Fi. There's sort of FQ analogs. There's actually 2 of them, slightly different ones. In characteristic 0, we have a nice stability result. Kind of, the same multiplicities don't depend on n past some point. In non-defining characteristic, there are some papers out there that start to prove some things, and we're starting to understand it, but I think there's still a ways to go. And defining characteristic, it seems super mysterious and interesting, and there's just behavior for these categories, VI and VIC in defining characteristic that we just don't really see for the symmetric groups or other families of groups that have been analyzed. And so it seems like an interesting thing that I am hoping to better understand. And then finally, other families of groups that are of interest, braid groups, arithmetic groups, and more. There's lots more. And in a lot of these cases, especially the braid group and arithmetic group cases, there are already in the sort of representation stability literature kind of topological and applications or incarnations of these kind of FI type categories and appearing for braid groups and for arithmetic groups. And it suggests that there should be some sort of theory on the representation theory side to go along with it, but it's sort of not there yet. And so I'm very interested in these type of stability questions for braid groups and arithmetic groups, because it's sort of open territory. Yeah. All right. I think that's it. I think that's all I wanted to say. So thanks for listening.
Thanks very much for this beautiful talk. Right. Is there any questions?
Can I ask a question? So if you look at modular representations or even representations of finite groups of Lie from a geometric point of view, I mean, you'd think that when n goes, say GLN, when n goes to infinity, you have an affine variety, and in some sense, what's hard or where things are happening is in middle dimension, say variety dimension n is an nth cohomology group that's hard. So when n goes to infinity, I mean, would that difficulty disappear, or I mean, have you thought of that?
So I will say this sort of thing. It shows up a lot in similar things in kind of topological settings. The reason why we can really say anything is that we're sort of, these sequences of representations that I'm claiming kind of stabilize or become periodic, they sort of have fixed like degree in some sense, and then n gets larger and larger. So I would say the reason, so these sort of middle homology degrees are sort of the unstable part. And that's the hard part. So this would be more like, if you look at things living in sort of fixed homological degree, you should expect to see this type of stability that I'm talking about. And then kind of all of the hard stuff lives in the more middle degrees, and that's unfortunately sort of not something I can get at by this theory.
No, but that's good, because somehow there are many questions that have no answer, and maybe it's possible to provide answers to stable versions of these questions. That would be very interesting. Yeah.
That's definitely something I'm very interested in, and yeah, there are certainly a lot of things where the answer is somehow easier in the stable answer than in the unstable one. At least by that I mean even in characteristic 0, with their sort of maybe combinatorial questions one can ask, and often the stable answer is actually easier than the unstable one. So I would hope to see that sort of phenomena for some more modular representation theory questions, but I don't know.
Have you looked at all at strict polynomial functors?
Yeah, so strict polynomial functors certainly appear, and that's, I mean, sort of, I kind of alluded to it a bit, and so Yeah, so strict polynomial functors, I would say, are sort of a stability phenomenon in the kind of strict sense, in that.
Yeah, we have stability results for cohomology and whatever.
Yeah,
But
exactly.
maybe it's a stricter sense than your sense.
I think it's very related, and
I don't quite understand it, but maybe it's a stronger condition.
Yeah, I mean, part of it is some of the things I was talking about are kind of vague, and I will say for some of these topological applications and things I'm interested in, the polynomial functors, strict polynomial functors, are not quite good enough because they can't. You don't have like the dual of the defining representation. It just seems like an empirical phenomenon in a lot of these kind of topological applications and stuff, that you really want kind of both the standard n-dimensional representation and its dual. And that's something that is sort of not in the usual theory of strict polynomial functors. And that's really where the kind of periodicity comes in instead of the stability. So that's, yeah.
There's also in strict polynomial functors, you can look at other types, orthogonal symplectic. And that seems natural for you to do as well.
That's absolutely right. And that I sort of stuck to type A questions.
Yeah.
And people certainly think about other cases. I would say, especially for the kind of applications that a lot of the people in representation stability had in mind, I think symplectic groups are an especially important case. And so both kind of finite symplectic groups and something like the integral symplectic groups are kind of a very important family of groups for the type of applications people care about. So yeah, I kind of avoided leaving type A today, but there's certainly a lot of interesting questions in other types.
Related to that, Nate, do you use like, you've been using Deligne categories, but do you use like the existence of GL infinity webs or in your stuff?
So the statement I said, this sort of periodicity for GLN is really a statement about GLN webs and GL infinity webs. It's you really like you kind of prove it combinatorially using webs for tilting modules, and then you kind of do a bit of algebra to say that if the categories of tilting modules agree, then kind of that you can enlarge that equivalence to a larger abelian subcategory.
And so for this periodicity stuff, you also wanted duals, you said? I mean, we're working on a diagrammatic category that for GL infinity, essentially, that has both V and V dual.
Yeah. So this GL infinity, this difference between the GL infinity and the Deligne category version is important because you want the dual to be to exist, to be a two-sided dual, and that imposing that condition is maybe what the difference between a Deligne category and the category representations of an infinite rank thing. So yeah.
Will type C webs help you? Because we're also working on that. C infinity.
I would certainly be interested in seeing them. I mean, I kind of always keep up on what is happening in the web world, mostly because I have my own sort of independent motives for understanding them. But yeah, type C webs are something I'd be into.
Just a comment. These truncations that you're talking about, these less than or equal to k, they should be kind of some instance of this Lustig's philosophy of generations. And then, I mean, there's this expectation that these generations are connected to questions in homotopy theory. And in homotopy theory, you have exactly that, the kind of, I was just confirming this with Jesper in the chat, but the Morava K theories become, they're always periodic, but the periodicity gets larger and larger, which mimics the fact that, you know, as you go deeper into this filtration, your periodicity becomes larger and larger.
I don't know anything about that, but I would love to.
Because in, like, for example, in this billiards, you can see this this periodicity, and it's rather fascinating. So
you go back to the slide, maybe then we can, yeah. So.
Which is.
Can you say how you see the periodicity of the billiards, Jody?
like basically, so where do we, okay. Exactly, so part 2 is the, so in the billiards, there's balls that go off and they bounce around. And somehow if they're if your ball starts too close to the other wall, then it can have some interference from that other wall. But once it starts out far enough along one of the walls, its behavior is independent under further translation along that wall. And so if you take a decomposition number along a wall and then translate it further and further out, you always get the same answer. Like if you translate it out by P, which is the kind of, this should be your periodicity or the first layer in your filtration. But if you look at decomposition numbers that are further away from the wall, then you can expect higher generational behavior to start kicking in, and that's when things get ridiculously complicated and we don't know what's going
on.
So,
I have a question.
Yes. So Jody was mentioning being away from the walls. So I don't know if you know the work of Schwang and Turner, which unfortunately I think none of it is published. They've been only giving talk about it. So you fix one of the weight is combinatorial invariant for a block, and you let P vary. And there's something also, a game with N, that's a different game. But the idea is that if you're far away from the blocks, from the walls in some sense, so the part of decomposition numbers for the symmetric groups that's going to stabilize. Are you aware of that? It's related to what they call cubist algebras, this work of Sean Turner called cubist algebras. So it's very much related to what Jordi's saying. It's kind of a, yeah, it's similar philosophy, but much simpler, and it's in the traditional first generation framework.
And you're letting P vary as well in that picture, you said?
Yes, the idea is that the part, it's like a cache diagnostic polynomial. They don't see P. Okay, it's a similar aspect.
Yeah,
so
that sounds more similar to the kind of this picture on this slide.
Exactly.
Yeah.
But it defines. You really have. They have identified. It's a bit more like your previous result. They identified a category that is expected to become somehow independent, and it's part of an infinite category. So it's a bit like maybe this Deligne thing direction as well. So you have a huge category, and inside you'll have you find something that's growing with maybe with N or something like that.
The voice from the deeps.
So I have a question. I wonder whether your approach would give us some way to get a better low bound on the dimension of the dimension of the model D lambda square bracket N.
Of D lambda square bracket N. So yeah, so we know, well, we know that these dimensions are polynomial on residue classes, and that Yeah, so I mean, so it's sort of computing those dimensions is roughly equivalent to computing these decomposition numbers, and yeah, so I mean, I kind of hope that that the answers in this kind of stable range are maybe easier to compute than kind of the general problem, but it doesn't sort of come out of the ways that I prove this like a good way of actually getting at them. So I don't know. But
so like so Sasha Klershev and Lucia Marotti and we put some bound which is explicit, and yeah, so it's basically we show that what should be the bound on the dimension of this module, but so I think the magnitude is right, but we have some term in the bound that we think that should be improved, but you don't know how to do it. So I was wondering whether maybe Yorizan can shed some light on it.
Or I think one of the things that a result like this gives is that you know if you compute one of these decomposition numbers kind of for one value of n, you kind of automatically know it for infinitely more values of n, and it sort of cuts down your calculation a lot. But
is that true, Nate? Because how do you know that you're stable?
It stabilizes like soon. Like yeah, I know when it stabilizes.
Oh, okay.
Explicitly?
It's roughly, you need n to be if I have this partition lambda, you need n to be maybe bigger than 2 lambda or 3 lambda or something linear in lambda is all that you need. So it's not it's not it's effective. It's this this happens sort of right away. But yeah, I at some point I had written down a bunch of these dimensions of the d lambda n's. They're polynomial in n, or pork rather, and I worked them out in small examples, but I couldn't. I at least couldn't find any nice patterns beyond beyond these periodicity things. And so I sort of think that, though, computing this stable decomposition number for this s for an s lambda of n should be as hard as or maybe comparably hard to doing it for the difficulty of the calculation should depend on the size of lambda and not on n. So it still might be like a similar type of calculation for computing decomposition numbers in general, except that you're doing it for a much smaller symmetric group. So it's still a hard calculation, but it's at least you're cutting it down, I guess.
Well, I mean, to find the low bound, you don't have to find all the numbers explicitly, but you just need to get some upper bound on the decomposition numbers, and also the bound of Sasha and Lucian and me. So we have it when your n is like at least 3 times the size of lambda. So that's something like that. Yeah. But maybe if you can improve it, that would be great. Yeah.
Yeah, I'll take a look.
Are there still some questions? Okay, so let's thank Nate again.